This is a production of Cornell University.
So let's start talking about this cycle. This is the nitrogen cycle. And this slide is rather complex. Okay? We're going to break this slide down and I'm going to simplify it. Okay? But in essence, this is the nitrogen cycle. Every one of the boxes basically is a pool. Every one of the arrows is basically a flux. Okay? The direction of the arrow indicates what direction the flux is going. Okay? From what pool it's moving into. From where it's coming and where it's going. Okay? Now, if we look at something like that, we have a couple questions that we need to think about. The first question is, what are the pools? What are the specific pools? Okay? And where are the sources and losses in those pools? Also, what are the fluxes between the pools? Which will sort of direct these issues of sources and losses. Okay? Now, when you think about these controls, the flux rates and the pools are often controlled by adaphic factors, the factors that are happening at that location. But the end sources are often global in nature. Okay? Like the CO2 here, this CO2, the flux rates and the pools that we're seeing here are very local. But that CO2 is very global in nature. That's the atmosphere. Okay? Well, that's the case with all of these nutrients. All right, so if we're talking about global, let's actually talk about where these pools are. Okay? This is not from your book. I pulled this from a nutrient book. Okay? But basically, this tells the inventory of nitrogen in our four spheres. Okay? The biosphere, the lithosphere, the hydrosphere, and the atmosphere. Okay? The largest pool, if you're talking about nitrogen, the largest pool is in the lithosphere, in the rocks. Okay? The core of the earth, the sediment, the coal, seabed materials. Okay? Very small pools. Then you actually look at the terrestrial soil component, very small pool. The second largest pool behind the lithosphere is the atmosphere. Okay? Nitrogen gas in the atmosphere. We also have the hydrosphere, fairly small pools, and then we have the biosphere. That's us. Very small pool. Most of the nitrogen on our planetary system is in the rocks. The second largest pool is in the atmosphere. Okay? So that tells us where it is. But we're more concerned about what's going on locally. So where in the biosphere and the sort of in us and in the soil N, where is that nitrogen coming from and where it's going? Okay? Now this is the nitrogen cycle that was in your book. Okay? You notice that it's getting a little bit simpler. Okay? Again, all these boxes are the pools. The arrows are the fluxes. So what are the sources into the pedosphere? There's basically 5 sources. The first is biological nitrogen fixation. Fixation of nitrogen by biological organisms, N2, into an organic form, ultimately into NH2, the amine form. We also have fertilizer. Now this could be industrial nitrogen fixation where we're intentionally doing this for fertilizer, but it also can be emissions. And I'm going to talk about these two a little bit in a few slides. And the reason I'm going to talk about these two is that these two are primarily the ones that we have somewhat of a control over. Now, we also have lightning. Actually, the bolt of lightning will react in the atmosphere and basically create a natural source of nitrogen that it's usable for in the soils in the pedosphere. Okay? And that basically accounts for about 5% of all natural sources. We also have off-site organic matter additions, i.e., organic matter is in one location and the wind blows and it takes that organic matter and moves it to another location. Well, the nitrogen that's in that organic matter is going to be moving from the first location to the second location. And then we also have the issue of dust. Nitrogen actually literally moving in dust, much like off-site organic matter additions. Okay? Let's talk a little bit about these two, just to give you somewhat of a perspective. If we start looking at what type of organisms, where this nitrogen is coming from, There is a number of different organisms that have the ability to take nitrogen gas and convert it into biomass. Okay? Now, nitrogen gas, N2, is nitrogen gas. Okay? Now, interestingly, it's a triple bond. There are 3 bonds holding those things together. Now, for organisms to use nitrogen, we need to have it in this form, an amine form. Okay, now this is going to be attached to a larger organic molecule. Okay, but we only need one of these. But this is triple bonded. This is really well bonded together. It's a tight bond. For organisms to break that bond, it takes a lot of energy. Now think about this. If I'm an organism and I have nitrogen in another form that's available for me to use, that's all around me, would I prefer to break this nitrogen, which is going to take a lot of energy to do, or would I rather take the easily available nitrogen that's in another form than this? Yes, it's in another form than this, but I can take it up and I can assimilate it. I'm going to go with the easy route. So it turns out that this ability to convert this to this has a sort of a select environmental control. This is a huge, if you can do this, this is a huge advantage. But it's only a huge advantage when other forms of nitrogen are not available. Does that make sense? So as a result, I don't know if this is actually the result, but it turns out there are very few species of organisms compared to the large pool of organisms that are on the planet that actually can do this, that can do the nitrogen fixation. Now, some of these are free living. Some of these live in symbiotic relationships with other organisms. Okay? Some of them, this is the whole sort, not all of them, but this is a huge slew of these different type of organisms. And it basically gives you an idea about how much nitrogen, N2, they're fixing, or kilograms per hectare. So in some cases, it's rather small. In some cases, it's rather large. Okay, make sense? Just to give you an idea what this distribution is. The other big source of nitrogen is fertilizer. Okay, I threw this in here basically to give you an idea about how, this is basically the green revolution. But it gave you an idea about how much more fertilizer, or the increased use of fertilizer we've seen over the last few decades. Okay? Basically, sometime in the middle 1960s, we started having the green revolution, which was basically agriculture through fertilizer or through chemistry. Basically, we saw a lot of nitrogen fixation going on from an industrial sense. This nitrogen was then fixed and started to be used. Okay? Now, this is a slide right here where you can see a series of crops. You can see the green crops back up here versus they're green too, but lighter green. This is a direct response of nitrogen fertilizer. More nitrogen fertilizer was applied here, less here, and as a response we had greener crops, more productive crops. Okay? Now, it doesn't say how, in this case we're talking about an artificial fertilizer that's put in, an industrial fertilizer, but in general, when you see more nitrogen in the system, no matter what the source is, you're going to have a greener crop, more productive crop. Okay? And you can see that response. This is nitrogen, phosphorus, and potassium. Okay? This is the green revolution. Okay, questions? Go.
For the before this, where you were talking about plants that can fix, I understood that it was bacteria or a symbiotic relation. It's not actually the legumes that fix the nitrogen.
These are symbiotic relationships. Some of these are symbiotic. Some of these are free living organisms. And it's not just legumes, but there are a number of other types of plants that are out there that have these symbiotic relationships. It's a microbial population that's doing the nitrogen fixation. The plants themselves are not. The microbial population is, and the microbes are supplying nitrogen to the plants, and the plants in turn are supplying carbon energies to the microorganisms.
So then this is how much of those organisms these legumes can support?
This is a list of the type of legumes: soybeans, cow beans, clover, alfalfa, lupins. And this is the amount of nitrogen that these guys range from fixing in this symbiotic relationship. Sorry, thank you for... We feel good with this? Do we feel good with this? No? Yes? Okay. Now, this is intentional fertilizer use. But we also have unintentional fertilizer use. This is emissions, in essence. Now, you've seen this slide before, but you've seen it in a different form. When I was talking about acidification and I was talking about acid rain, you had a slide that looked basically like this. Now, I'm talking about emissions. This is an emission slide. Where's it coming from? It's coming from the same stacks that are throwing up the acid rain. The stacks are basically burning coal, and in that coal is sulfur and nitrogen. Okay? In this example, we're looking at nitrogen. Okay? But that nitrogen goes up into the atmosphere, and it mixes with water, and it basically makes nitric acid. Okay? That water comes down as rain, and we acidify these environments. But it's a nitric acid, which means it's nitrogen coming down. So at the same time as we're acidifying these environments, we're basically fertilizing them. And this is a map of that fertility. Basically, we're looking at the Ohio Valley and the power plants that are sitting up in here, the wind pushing things this way, and we're seeing the downwind response of that nitrogen hitting the ground. Yes, we're acidifying, but we're also nitrifying. We're fertilizing and acidifying at the same time. We're fertilizing the world. But this is a good example of that pattern. Okay? And we control this. Okay? Questions?
So the concentration of emissions in this like kind of central to northeastern America is caused by like
Power plants.
density?
Power plants. Coal-fired power plants are the major driver of this. Now, it's not that we're not going to have emissions all other places, but this is where the concentration, this was where the industrial base of the country was, and this is where they needed the power.
This has been a production of Cornell University, on the web at cornell.edu.